Have we talked about standard error?
We haven't talked about standard error versus standard deviation. That's an important piece to come, which actually we should start talking about that. We need to talk a lot more about that when we get to bootstrapping. It's almost obvious, but it's so obvious that it doesn't frequently get dwelt on how important the difference is. So yeah, let's talk a little bit about that. Standard error versus standard deviation is like something important. And we have the tools to start talking about it from the normal distribution, but also that. So let's finish talking about probability distributions. And then we'll start to talk about standard deviation versus standard error. At least that's the word. Those are the words that I use for them. I think some people also call this the standard deviation of the mean and things like that. So we'll just be clear what we mean. I think I'm consistent in the notes with how I say it anyway. Okay, so one thing we skipped over yesterday was how you count things, like how you get the binomial distribution and all those pieces. And then it's kind of a nice little set of things to go through. So, like, we talked about rolling dice, we talked about cards. They're useful because what kind of a distribution do they obey, at least in the first draw?
Uniform.
It's a uniform. So it's uniform to get flips of the dice, uniform to get flip of a coin, roll of a dice, draw a card from a deck. There's a uniform probability on the first one. What about the second one?
Still uniform.
It's still uniform, but it's uniform on a different set, right? If you're not putting a back end every time into a deck, you're actually changing the probability of what's left each time you do it. Then, we don't actually have a whole lot of games that are like this, but like, if the sequence in which things happen is important, that's really different than if the sequence is not important. So it's much harder to roll dice and get 1, 2, 3 in that order than it is to get a 1, a 2, and a 3 in any order. Does that make sense? So there's a couple of nice little counting rules that help you count those kind of things and help you build those kind of pieces. So I thought that's kind of a nice thing to do, which isn't exactly the probability distributions of like the binomial distribution or anything, but it's the building blocks of those. So it's kind of nice to know them, and we've seen some of those pieces. So what's the probability of getting any one possibility out of a uniform distribution of n things? Just what's the probability of getting any particular one out of n things? 1 over n. Okay, so the probability that you draw 1 of n things is just that. Okay, so that's like flipping a coin, rolling dice, whatever. And in the Bernoulli test, you could actually change this a little and make, like you could say, suppose the heads are more likely than the tails on flipping a coin or something. You can weight it differently in that test, but we don't have to worry about that right now. Let's just assume uniform. So cards are dice. Okay, so suppose we roll the die again. What's the probability of getting a particular outcome on both the first and second? So roll it once and get a 3, roll it second time, get a 5. What's the probability of that?
1 over 36.
1 over what?
36.
1 over 36. So it's this times itself. It's the same odds to get for the second one, and because the order is important, it's the same. So in fact, the probability of any particular ordered outcome, I don't know, I'm going to take it like that. Getting it n times in a row is 1 over n to the n. Okay. Now, suppose we're doing cards and we don't put the card back in. So the first card we draw, what's its probability? So this is replacement. With replacement. Without. Okay, what's the probability of the first card?
1 over n.
Same. Okay. What's the probability of the second card? Or the first two?
1 over n times n minus 1.
1 over n times 1 over n minus 1. And we can keep going, you know, dot, 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 1 over n minus 1. So what's the probability doing it little n times with big N things?
Just 1 over n factorial. Big N factorial.
Not quite, because there's like, this one is part of the factorial, the part that goes from big N, to little n. So it's n minus r factorial over n factorial, and now I've totally changed all of them. Let me make sure I figure out what it's about to see. Using different notation. Bootstrapping is the first R cards of the shuffled deck. Alright, so let me be consistent. My notation, R of those, N of these. So this is the one that's going from the total number down. So this is the total number of cards. Little n is the total number now. And we draw R things from it. So we only go down to R. So n minus R factorial starts the next, starts at that one and cancels it out. Does that make sense? So it's like, then this would be times, R minus 1 over R minus 1, and that one goes out, and so on. That's these guys. Does that make sense to everybody? Okay, so these are still preserving the order. So these are called permutations. This is like digits in a number. The sequence matters. What happens if the sequence doesn't matter? How many ways are there to sort them? If we no longer, suppose we have 3 things. How many ways can I sort them? Like, we got A, B, C. We've got 3 slots. We got slot number 1, slot number 2, slot number 3, and suppose we have 3 things to put in there: A, B, C. Then we can go A, C, B. The other ones that B, A, C, B, C, A. How many more have I got? C, A, B, C, B, A. Is that all of them? So how do we count those in general?
So I think what you can imagine is you can fix one of them and then imagine the rest of them are just sorting, I guess, 1 less, so it's like a branch.
Exactly. So we pick the first one, and then our choices are limited for the second one. And then our choice is really limited for the third one. There is actually no choice for the third one. So how does that work in terms of factorials? So how many ways are there of picking the first one? 3. So that's the number of things we have. We could have picked any one of them. So let's be clear about which one's which. This is always the one that I can get confused on which comes. Okay, so there are n things, and I'm going to choose r of them. So of the n things, I choose r of them. So that's n choices, because they're n things for spot 1. Now, how many do I have for this one? For the next one. I've chosen one thing. How many things are left? 2 things. So how many is that? How many choices do I have for slot number 2? Should have been different number of slots, but anyway, whatever. How many choices do I have for slot number 2? 2. I've already picked one. So I can either choose B or I can choose C, right? So it's n minus 1 things. How many would I have for the next one? If I had more than 3, if I just kept them. Or how many do I have for 3? Once I've chosen this one, once I've chosen this one, how many choices do I have for this one? There's only 1 left. So I don't need the last one. Okay, so in general, the thing that we're after is the combinatorial of n things, choose r of them, which is sometimes written like this. And it's n factorial divided by n minus r factorial, r factorial. So comparing between this guy and this guy, oh, sorry, that's the number. Sorry, this is the number of things that are like this is 1 over that. So n factorial over n minus r factorial. This is the number of possibilities. So compare the number of permutations to this. What's the difference?
There's a factor of 1 over r factorial there.
So what does that represent? Which number is bigger? The number of permutations or the number of combinations? Number of permutations, yeah.
Can I just ask, like, not on the mathematical level, but what is the difference between doing it without replacement and then, like, going down by 1 on the number of possible options?
It's very, very similar, except here, the way we're not allowed to switch the one that goes in number 1 and the one that goes in number 2. Once we've chosen one, we have that one. So here we're doing that same thing, we're choosing, but then we're also making, let's see, the ones that, all 6 of these are the same in the combinations, but they're different in the permutations. Does that make sense?
Yeah.
So permutations order matters, combinations order doesn't matter. And actually, so r factorial here is, since it was choose 3 factorial is 3 times 2 times 1, so it is 6. So this dividing factor here is actually these 6 combinations. Right? Does everybody get that? So what's the r factorial? So what is that, this extra factor, what does that tell us? It's the number of equivalent rearrangements when order doesn't matter. Does that make sense? So in this kind of case, order does matter. In this case, order doesn't matter. And because those formulas are so similar, you're like, oh, they're exactly the same. But in this case, there is this extra piece which says that must be the number of possible ways of rearranging. That makes sense to everybody? And the magical thing about these, which is a little harder, is what if there are 3 slots but only 2 different things to choose from and that kind of stuff. You can play with these formulas and do, wait, which ones are equivalent? Is it A, B, B equivalent to A, B, A? You can start counting and making yourself crazy with all this stuff. It's kind of fun. But these formulas work once you interpreted them, even for those cases correctly. Okay, so how do we use these counting pieces to get to probabilities? Like, what's an example of creating a probability out of either the number of permutations or the number of combinations? That's the number. How do I get to a probability from that? Let me ask this a simpler thing. So suppose we say, in each of these, when we played this choosing game, is any one of these preferred over any other? No, that's sort of the setup, is all of these are equally likely. So if we have however many, doesn't matter what they are, forget what their labels, forget how complicated they are, we have things and they are equally likely, what's the probability of getting any one of those things? One over the number of things. So this count of combinations is just 1 over that is the probability of any one of them, if every combination is equally likely. This count of permutations, 1 over the number, which is this one, in fact, we actually wrote it that way, probability is equally likely. This one, if there are n things, 1 over the n things is equally likely. So in each of these cases, we're building a uniform distribution of the set of possible states. Does that make sense to everybody? So that's kind of the framing way of how dice rolling works, how drawing a card works. Even if we're drawing multiple cards, we still have a uniform large number of possibilities. That's what these help us count. Okay, but now, so our histogram of all the possibilities would just be even over time. What if we now start paying attention to which card we draw or which die number we roll? So, you know, in craps and other dice games, you add together the number that comes up from both of them. Does that change the likelihood?
The likelihood of a sum?
The likelihood of a sum, rather than the likelihood of possible outcomes. So we've talked about, so what if we roll a die twice? How many possibilities are there? 36, bing, bing. How many possibilities are there if we don't care what the order is? Wait, so let's do that one. Okay, we want to do, so I have n possibilities, which on a die is 6. I'm going to choose 2 of them. I'm going to roll it twice. Okay. What does this give us for that? So the number of permutations. Oh, without replacement is a little complicated thing in dice. And that one is 2. We actually don't have the reordered with replacement contemplation on the board yet. We only have the reordered without replacement. Let's think it through. So, okay, what are all my possibilities here? 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Which one of these would be the same if I allow reordering?
1, 2, and 2.
This one, and this one for now. And then I can go 3s, 4s, 5s, 6s. I don't even know how this is going to work out. I'm going to write it down and see. 3, 6, 4, 1, 4, 2, 4, 3, 4, 5, 4, 6. No, what do I say? 4, 7, 5. 1, 5, 2, 5, 3, 5, 4, 5, 5, 6, 6, 6. Okay. So how many do we reduce the number by? We have 1, 2, and 2, 1. We have 1, 3, and 3, 1. We have 1, 4, and 4, 1. We have 1, 5, and 5, 1. We have 1, 6, and
Oh, we didn't do 6.
6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 1. So how are there any triples? No, they're only pairs, right? So every time I have two different numbers, I get a reduction by a factor of 2. Every time I have a single number, am I getting the reduction? So there's a subtle difference between whether I roll the same number. If I roll the same number, rearranging them doesn't change the number between the permutation and the combination. But if I have different numbers, then it does. So there's a slight difference there. So in this one, I wasn't allowed to repeat. In this one, I am allowed to repeat. So there's slightly fewer, there's a slight difference between the number of combinations with replacement and permutations with replacement than there is permutations without replacement and combinations without replacement. So everybody see what I mean? This is sort of like divided by 2. It's almost the possibilities divided by 2, except it's not, because these guys, all the ones that are different numbers are going to have a partner. Does everybody see what I'm after? So the number, this number is p to the n. That's the number of things doing it that many times. Sorry, let's update this to our equivalent notation. R, little n, R. So the number of possibilities with replacement is p to the r, which is 1 over n to the r. So I roll a dice, however many times, there's 6 possibilities. Now how much of that do I lose when I cancel out all the ones that are the same? Nothing. But how many ones are the two different?
Aren't they the same 1/6 of the time? There are 6 out of the 36 options.
Yes, exactly. So there are 6 out of the 36, wherever they are, that are the same. So there are 30 where they are different. So how do we write that? What's that proportionality?
Proportionality of
The ones that are the same to not the same.
Yeah, the ones that are the same to not the same. Yeah, so it's 1/5, or I think it's n minus r plus 1 over r plus 1, or something like that. I don't know. There's a complicated factor that we could say, that we could probably figure it out in general for n's and r's by playing this counting game and saying how many are the same in the permutation and the combination, how many are different in the permutation and the combination, and then in the combination, how many differences are equivalent when you reshuffle. Does that make sense? So it's the same as this game, but it's a little harder when we have duplicates, because we have different counting categories for the duplicates. Everybody starting to see how this goes?
So you're multiplying by some ratio in order to account for the duplicates.
Exactly. So in this case, it was easy. We multiplied by 1 over r factorial, which accounted for the number of times that I would have equivalent answers, which in this case was 6. Right? So we need an equivalent ratio here, which is the number of times that reordering reduces my fraction. So in this case, we agree that this factor should be 5/6. But I'm not actually sure how to write it down in terms of the factorials to get it right. That would be a fun thing to think through. Does everybody understand? Okay. But now let's play an even harder game, which is the game that starts to relate to standard error versus standard deviation. How many of these have an equivalent sum? Let's actually just make a histogram. This is the sum of the rolls. What's the least sum I can have? So I got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Can I have 13? Yeah, so I can stop at 12. Okay. How many 2s do I have? Exactly 1. Snake eyes. How many 12s do I have? Just 1. How many 3s do I have? 1, 2, and 2, 1. So I have 2 3s. I also have 2 11s. How many 4s do I have? 1 3, 2 2, 3 1. Is that it? Ready to see what I'm doing? So each of these was a uniform distribution for the rolls, the different permutation possibilities, but what we are charting now is definitely not a uniform distribution. What's the 5s? 1 4, 2 3, 3 2, 4 1. Is that all of them? And the 9s will be the same. How many 6s are there? 5. 1. I don't even know. All right, I'll go with 5. 3 4 5. 1 2 3 4 5. And how many 7s? We got 1, 2, 3, 4, 5, 6, 7s. So when if you're playing craps, the 7 is the one where the house wins, and the 2 is the one where you win. So you can now see why they have chosen this particular game. And the particular rules of the game are tilted in a way. It seems like they would be uniform. If you were rolling 1 die, and the 6 wins for the house, and the 1 wins for you, it's a fair game. If you're rolling 2 and adding them together, the house has a major advantage. Does everyone see how that works? So we started with something that had a uniform distribution, and what do we do to get a non-uniform distribution? Let's go back to the permutation versus combination. We started with something that had a certain number, and then we did something to change the number. What do we do to change the number?
We now have a certain number of roles.
We equated some of the combinations, like things in different ordering. We said there's a lesser number. In this case, we've added a quantification which has now equated some of the classes, but in a non-uniform way. If every class has a quantification that's equal to the number of classes, then it doesn't change the probability distribution. But if some of these can be considered equivalent in our metric in this case is the sum, then we have transformed the distribution because we're now combining bins together. Does that make sense to everybody? This is the difference between the standard deviation and the standard error. So the standard error is a distribution of the mean of a set of observations, and the standard deviation is the distribution of another observation with a given initial distribution. Okay? Do those two things have the same distribution? No. We just did an explicit example where we started with a uniform distribution of die rolls, and then we took the sum, but basically we could have divided by 2 and it would have been the mean. The mean of those things will have a different distribution from the original distribution of what the single die roll was or the double die roll. So the single die roll has a uniform distribution of 1 out of 6. The double die roll has a uniform distribution of 1 out of 36. But the distribution of the average of those two rolls has a distribution that's like peaked in the middle. So when we take a set of observations, we need one quantity to describe the likelihood of getting different observations from among the set of possible observations. That's the standard deviation. So how do we calculate standard deviation? It's the square root of the variance. So in this case, well, we figured out yesterday what the variance of a uniform distribution was. Does anybody remember what it was? I don't actually remember. I have it all nicely calculated, except I can't find the paper. You think you have to do everything you want to have. Well, how do I find the discrete uniform distribution? Here we go. The statistics of the discrete uniform distribution, so this guy or this guy, these are both discrete uniform distributions. This one has more values in it than this one, but that's what we meant for both. Is the mean is the max plus the min over 2. So what's that for dice? So 7 over 2, exactly. So it's just the average. For 2 dice, that's a little hard because we don't actually have a definition of what we mean by value of these things. it every number, only once? So this is not a uniform distribution from 11 to 66, right? Because we're missing digits. I should have 17, 18, 19 if I was going to, 20 if I was going to build that up. So we can't use this trick for this one. We need to assign these. But if I assign these a number from 1 to 36, what would the mean of it be?
37
37
over 2.
over 2, exactly. So we could use this in that case, and we just gave each of these a number sequential. All right, what's the variance? Or, sorry. Variance should be x squared minus x squared. That one is a max minus min squared over 2 over 12. Ah, more fun. Over 12. Is that right? Well, let's check it. Might be over 2. How would I figure this out? How do I calculate these objects? Well, this one, how do I calculate it? I just square that one. What about this one? How do I calculate the moment of a distribution?
Oh, well, I see where my mistake is anyway. It's not 12 in this case. It's just some horrible thing.
I will tell you, the answer to this one is that you need to take the sum of all of the squares minus the sum of all the values squared over n. And so that's the thing you have to do, which is how you would calculate it. But I don't think there's a simple formula for it. It doesn't factor. So what is this then for rolling the dice? We have to add 1 plus 4 plus 9 plus 16 plus 25 plus 36 minus 3.5 squared, right, over that. Or 3.5 times 6, whatever that is. The sum of all the dice. And then divide by the number. So we can calculate this once we have the numbers, but that's what we have to do. Okay. These things do not relate to this thing. Right? Once we've taken this sum, we have now put a new measure on each of these values, and some of them are equivalent. So the standard error tells you about this guy. The standard deviation tells you about this guy. So the deep reasoning for this, the reason why this is important is, so why do we take more than one experiment and then average them together to try and measure an answer? Like, what's the point? Why would we do that?
So there's just like random variability.
Sure, there's random variability. So each time you make a measurement, there's some standard deviation of those measurements. This guy. Why does averaging help us? What happens with those random errors?
Ideally, they cancel out.
They tend to cancel out. So in this case, the random errors had a distribution that looks like, this, uniform. What does the average have a distribution? It's narrower. If I took 3 dice and did this, you would have gotten narrower still. If I took 1,000,000 dice, it would have been almost a spike at one value. So if I roll a dice 1,000,000 times, does it affect the probability of the 1,000,000th and first roll of the dice? It doesn't. So every single time I roll a die, I got a uniform distribution I'm drawing from. But if I roll dice 1,000,000 times and average the 1,000,000, it is going to be extremely close to 3.5. Does everybody see what that is? So the standard error is the descriptor of the average. Standard deviation is the descriptor of the next experiment. And there is a thing called the central limit theorem, which we're not going to talk about now, but we're going to emphasize again when we come back for bootstrapping. It says if this one was a normal distribution, and this one was a normal distribution, the central limit theorem, and it says a lot of things. One of the things it says is that this one converges to the Gaussian distribution we talked about last time. When you have a lot of things and you put them together. You add them up. This distribution becomes a Gaussian, which is why the Gaussian is really important. Why, whenever you take, a bunch of students in a class, and they've all got different reasons for getting different grades, but if you average all of the grades, and you look at the statistics of the average, it's always a normal distribution, right? And every individual student is maybe having some crazy probability distribution of what their grades are. Like, I used to chart my grades were highly bimodal. The ones that exams I had in the morning, I did badly on, and the ones that I had exams in the afternoon, I did well on, just because I was poorly slept. So my own distribution was kind of crazy, and everybody has their own distributions, but assuming that there's sort of a prototypical student distribution, the distribution for the average grades across all the classes should have a normal distribution. Does that make sense? So the standard error tends to be a descriptor of a normal distribution, even when the standard deviation might be very hard to measure of something like uniform or exponential or crazy distributions, Poisson, whatever. Does that make sense to everybody a little bit? In the special case, where this is a normal distribution and this is a normal distribution, the standard deviation of the mean, so the standard error, is the standard deviation of the original distribution, x, divided by the square root of the number of observations. We actually can derive this, we will derive this later. But let's think about what this means in terms of repeating an experiment. Every time I repeat an experiment, do my errors go down? Well, maybe if I get better at it, but assuming that I didn't learn from my mistakes and just continued the same experiment every time. So every single experiment has standard deviation. Does my standard deviation of those experiments, is it expected to go down? I mean, it might go up if I go down randomly, but eventually if we do enough experiments, we're going to settle on a nice measurement error that is a good estimate of what our measurement error is. That's what this represents. But when I do more and more experiments, my result is getting more and more certain every time for what the average is over all that experiment. That's exactly what this tells you. So if you do 4 experiments, your answer is twice as certain as if you just did 1 experiment. If you do 1,000, 10,000 experiments, it's 100 times less uncertainty in the mean than there is in any individual experiment. So that's the difference between standard error and standard deviation. Yeah.
I know we used sum in this example, but is it just usually the case that standard error would only be describing the average, or can you use it to describe the sum or a different metric?
You could also say I've done error propagation.
Mm-hmm.
So I could, in this case, our function of x is the sum of x, right? in this case, this rule applies. In other insane things, so what if my function of x was, x, logarithm of x? This will not apply for this. You'd have to work out an equivalent translation formula to figure that out. So I guess it belongs. Or if it was the multiply them together instead of summing them up, you would not be able to do this error propagation formula. So this funny computational trick that we're going to talk about next week, called bootstrapping, helps you do this for arbitrary functions. So it isn't guaranteed to work, but under sort of not crazy circumstances, it at least gives you an estimate of what this distribution is like. You basically play a game where you try and make synthetic data from drawing out of your data that you actually have, and then build the statistics for the mean or the whatever function you're trying to perform on those statistics. And so the amazing thing is that this formula, I think we actually probably will do this out. This is written in the notes how you derive this. But in general, if this wasn't a normal distribution, we don't really know what this is. This one is always a normal distribution, that one's not. But go to a different function where this isn't even a normal distribution. This becomes something crazy. We don't know how to make this. We don't really know how to generate these PDFs. But with this special technique of bootstrapping, which is basically this drawing with replacement, this guy, we are able to synthetically build this system up. And under some normal circumstances, it does a decent job of predicting this distribution. We kind of do exactly what we did with the dice, except instead of dice, we actually have data. And each data point has a measure. Does that make sense? Okay, so let's stop there.